Hello, and welcome back to a new series that will go over the four basic ingredients for severe weather and where each of them come from. Those ingredients are lift, moisture, instability, and wind shear. All of these ingredients are critical in forecasting severe weather, such as hazards and risk levels. The ingredient I'm starting with today is lift, which serves as a trigger mechanism for thunderstorms. If you enjoy this video, I'd appreciate if you leave a like and subscribe, and we'll get started. The first thing to discuss on this topic are the scales of atmospheric motion. There are four different scales of meteorology, and those are planetary, synoptic, mesoscale, and microscale. The main two that we'll focus on will be the synoptic scale and the mesoscale. And I got a chart made up to explain the differences between the two scales, and we'll go through this before we go into the sources for lift. So, what does a synoptic scale consist of? Spatially, this ranges from 1,000 to 10,000 kilometers, and the time range is from days up to a week. So I'll illustrate some of the examples that I have listed below. And the first one here is mid-latitude cyclones, which is basically just your low pressure system. And so some of these low pressure systems can expand up to several thousand kilometers, which puts this on the synoptic scale. And you also have the frontal systems that are associated with your low pressure. So you have your cold front that extends down to the south, and your warm front. Ooh, let's put that in a different color. You also have your warm front here that extends out east of the low. And then you have your upper level wave pattern, which is your trough and ridge pattern, like this. That is on the synoptic scale. And then you have the jet stream that flows through your wave pattern. And so those are some examples of what we see on the synoptic scale. So now let's look at the mesoscale and talk about that briefly. So the first example we have are thunderstorms, which can be in the form of supercells or something like a line of thunderstorms, or like a squall line. And then next we have are what we call dry lines, and those are surface features that border hot, dry continental air that's coming off of the desert southwest over here on the back side of your dry line. And then you have moist air that's coming off of the Gulf on the other side of your dry line over here. And then next we have short waves that are kind of embedded in the flow of your upper level wave pattern, like this. Like this. And then last, you have tropical cyclones, which are also on the mesoscale. So those are the two main scales that we're going to worry about for right now. And so next we're going to move on to the sources for lift. There are about 5 of these on the synoptic scale, and a few on the mesoscale that we'll talk about. I'll start on the synoptic scale, and then we'll look at a case study, and we'll see what the influence is that the mesoscale can have on lift. And so the first source of lift on the synoptic scale is going to be the jet stream, which is located near the top of the troposphere. The jet stream you see illustrated here on my screen. It follows through your upper level wave pattern, and it is a river of strong winds aloft. And these winds will help create strong upper level divergence, which will then relate to the second source of lift. So what is upper level divergence? The best way to explain this will be to illustrate what we call mass continuity. So what is mass continuity? I have a diagram drawn up to explain this process that begins with the upper hemisphere at the top. When you have wind vectors that are splitting apart at the top left corner of the screen, that will remove mass and create a void in the atmosphere. The atmosphere doesn't like that void, and so it's going to bring up air from below and lift it to fill that void. The lifting of this air is going to decrease the surface pressure down at the bottom left corner of the screen, and winds are going to converge towards the center of that low pressure to fill that void. And so that is what helps create the rising motion as a result from the upper level divergence. And this process also works in the opposite as well. When you have winds converging in the upper levels, and this increase in mass at the top will cause air to sink below and increase pressures down at the surface. And the result from this high pressure down at the surface will cause the winds to spread out. And so that is the process of mass continuity, which is caused by the upper level divergence. The next source of lift is our wave pattern. On the synoptic scale, we'll look at the long wave troughs and ridges. The upper level wave pattern has the trough at the bottom of the wave and the ridge is at the top. For example, let's say Birmingham is underneath the ridge and east of the trough at 7 a.m. 12 hours later, that trough moves through and Birmingham is now on the inside of the trough. As you move closer to the inside of your trough, the height of 500 millibars is going to decrease, which will then force air to rise. The next source for lift is temperature and vorticity advection. These terms might sound fancy and complicated, but I'll break these down for you. First, let's define the term advection. Advection is simply the transport of a given atmospheric property from higher to lower quantity. There are three main properties that we associate with advection, and those are temperature, vorticity, and moisture. We'll discuss moisture in the next video, but for now, I'm just going to focus on temperature and vorticity. Let's tackle temperature advection. There are two kinds of temperature advection, warm air and cold air advection. Warm air advection fosters rising air, while cold air advection fosters sinking air. Warm air advection is in proximity to the low pressure, which we know from mass continuity dictates that air is going to be rising with low pressure. And cold air advection is associated with high pressure. And so that we know will create sinking air for mass continuity. So what is vorticity? Vorticity is the measure of spin in the atmosphere. Not to get too deep in the weeds here, but the mathematical equations that tell us that advection of this spin helps generate lift. Troughs and short waves are sources for this spin. The last source on the synoptic scale level is frontal lifting. And we're going to look at frontal lifting both on the horizontal and in the vertical. So on the horizontal, at the top of the page, you have your warm front and your cold front here. And your cold front is moving south of your warm front with winds blowing in behind it from the northwest, and then winds blowing in from the south of your warm front. So when the cold front meets this warmer air, that is going to cause your surface winds to converge, to meet together, and then that will force the air on the surface to lift up, which is why we call this frontal lifting. And so on the vertical, here's what this looks like. I have a rough sketch of what frontal lifting looks like in the vertical. So as your cold front is coming through, you have shallow. The colder air is pretty shallow, and then it gets deeper as you move to the west, deeper into your cold air mass. And so what this looks like in the vertical is this shallow layer of colder air lifts this warm air ahead of the cold front, and it lifts it up into the atmosphere. And so that is basically all we're saying with frontal lifting. And so that is going to be all of the sources of lift on the synoptic level. We're going to look at a case study here and show the roles that lift plays in forecasting severe weather. And we'll also use a case study to show some of the mesoscale features that were in play as well. So the case study that I'm going to use for showing lift is going to be the March 31st tornado outbreak from this year. And so just going to introduce this. This is a very widespread tornado outbreak during springtime of this year. And this tornado outbreak, I believe, is um, the third highest tornado count in a 24-hour period on record. This is behind the April 27th and the April 3rd super outbreaks. And so this was a very active day that expanded all the way from Iowa, Wisconsin, Illinois, and Indiana down into the Mid-South and Tennessee valleys. And this outbreak started producing tornadoes as early as 2 o'clock in the afternoon and kept going until 6 a.m. the following morning in Georgia. So a very long duration and widespread tornado outbreak from this day. And so we're going to look at some of the roles that lift played for this event. So we're going to look here and start at 300 millibars here in the upper atmosphere. And we're looking for the jet stream here. And so I'm going to scroll past here and go to around noon during this event. So we're looking for the jet stream, and it is located from New Mexico up into the Central Plains and Kansas and Nebraska. This is your primary jet stream up here. There's also looks to be a secondary branch of the jet that extends from South Texas up into the lower Mississippi Valley up here, and Tennessee valleys as well. And so this is the splitting apart of our wind vectors here. And this, in the in-between here, this is going to be our void here. And so this is what's going to be creating that uplift in the atmosphere. Is this void, the atmosphere doesn't like that void, and so it's going to be bringing air from below and to fill that void. And so that we know from mass continuity. So next we're going to go to 500 millibars and look at our trough ridge pattern. And we have a very potent trough here at around noon that extends from the Central Plains down into the Southern Plains. Well, let me redraw that. That extends from western Nebraska down into Texas and the Southern Plains. And so let's look at, let's go scroll back here. Let's go back to the morning of this 7 a.m. And let's look at Missouri. Let's look at Kansas City, Missouri. So Kansas City, Missouri is about right here. And so we're going to watch this 564 decameter line and 556 decameter line. And so let's watch for our height falls here. And so let's scroll to around noon. And then let's look and see if we have height falls here. And that we most certainly do. Here's Kansas City, Missouri, about right here. Your 564 decameter line and your 556 decameter line. So you have strong height falls over the Ozarks and from Iowa down into Arkansas, basically. And that's going to be moving towards the Mississippi Delta. And that is also helping to create the uplift in the atmosphere for severe thunderstorms. And so next we're going to look at 700 millibars, and this is where we start getting into the mesoscale. So we're going to scroll up here to around noon. And so we're looking for our short waves here on this level. So we have our primary short wave right here down from over the high plains. And then you have a subtle short wave. If you look closely over the Ozarks, it may be hard to tell, but there's a subtle short wave here from southern Missouri down into northern Arkansas. And this is helping to enhance the uplift in the atmosphere to help foster a round of severe thunderstorms. And this is, I believe, what basically initiated the tornado outbreak across the region. And so next we're going to go down into the surface and see our surface patterns. So we're going to go up to around noon. And so you have your surface low up in Iowa with a cold front extending down into Kansas, Texas, and Oklahoma, down into the southern plains, with your warm frontal boundary up through Iowa, Illinois, and into the Great Lakes region. And so that helps with the frontal lifting. And there's one more thing that I want to talk about on the mesoscale, and that's going to be prefrontal troughs or pressure troughs. They're both interchangeable. They mean basically the same thing. What those are is basically tongues of lower pressure that aren't associated with any frontal boundaries. And so I see two distinct pressure troughs here. One over the Mississippi Delta, and then another one that appears to be over the southern Ozarks, down into the Mid-South, down into kind of the Mid-South region from southern Missouri down into Arkansas. And so both of these prefrontal troughs help enhance the uplift in the atmosphere to help create supercell thunderstorms. So that's going to wrap it up for the lifting ingredient on this video. I hope you learned something from this, and you'll probably see this case study come up again, and I'll talk more about it later. Remember to leave a like, comment with any questions that you may have, and I'll see you in the next video.